Hello class, today's lecture will be on intermolecular forces. So what happens when an ionic substance changes phase? What is separated during the phase change? Well, if the red dots represent a cation and the green dots represent an anion, we know that cations and anions are pulled apart when an ionic substance changes phase. So, what force is overcome when the substance changes phase? Well, it's the electrostatic attraction between ions. From lab we know that that is a very strong force because we couldn't even get our copper sulfate to change phase with the heat from a lit Bunsen burner. Very strong force holding those particles together, resisting a phase change. Now let's consider a covalent substance. Covalent substances are molecules. They're not a lattice structure of ions. And so if I am changing phase, what is separated during these phase changes? Well, it will be the molecules of water themselves. Now remember, the oxygen and hydrogen is held together with a covalent bond. We are not separating that bond, but we're just separating one water molecule from the other. Now the question is, what force is overcome? And that is the subject of our tutorial today. Intermolecular forces, also known as van der Waals forces and abbreviated by IMF. These intermolecular forces only happen between molecules of covalent compounds, and it is a very weak electrostatic force, not strong like the ionic intermolecular force, the electrostatic attraction, or the covalent electrostatic attraction. It's very weak. IMFs come in many flavors. One is called the dipole ionic IMF. One is called the dipole-dipole IMF. Dipole-dipole IMFs can be further divided into the hydrogen bond, which is a specific kind of dipole-dipole interaction, and then we have the dispersion force. Let's get into dipole-dipole. Let's consider the molecule HCl. If we look at the bond in the molecule HCl, we'll see that the electronegativity difference is 0.9. So there is a dipole on that bond. Now if I look at what happens in between one HCl molecule and the other, I can see that the H will have the positive partial charge and the chlorine will have the partial negative charge. And these two molecules will be weakly attracted to each other by an electrostatic attraction. And this is what we call an intermolecular force because it's between the two molecules. So that's a dipole-dipole. Now let's look at hydrogen bonding. Hydrogen bonding is a specific case of a dipole-dipole, but in this case there is a hydrogen in the bond. So if we look at the electronegativity difference between hydrogen and chlorine, we see that it's really, really strong dipole. So that means that the force of attraction between the negative on one fluorine and the positive hydrogen on another molecule will be very strong. So hydrogen bonding is a particular kind of dipole-dipole attraction, but the bond has to be either a hydrogen-fluorine bond, hydrogen-nitrogen bond, or hydrogen-oxygen bond. Let's look at hydrogen bonding in some other molecules with hydrogen-oxygen or hydrogen-nitrogen bonds. So in water we see also a dipole between the hydrogen, intermolecular force between the hydrogen of one water molecule and the oxygen of another. So hydrogen bonding happens between water molecules. Ammonia, the same thing. The hydrogen of one ammonia is attracted weakly to the nitrogen of another water molecule. So these are particular kinds of dipole-dipole attractions called hydrogen bonds because hydrogen and nitrogen, hydrogen and oxygen, or hydrogen and fluorine are involved. Now here we can see that hydrogen bonding can happen in between two different molecules with nitrogen-oxygen or nitrogen-hydrogen bonds, and here's a case with water interacting with ammonia. So they will also have an intermolecular force between them because they're both charged. And this would be a hydrogen bond since we have oxygen-hydrogen attracted to the nitrogen of a nitrogen-hydrogen bond. Hydrogen bonding is really important to us in DNA. As you see, we have the weak electrostatic attraction, the intermolecular force between one nitrogen-based adenine and another nitrogen-based thymine. And this is really important because that means that the DNA two strands of DNA are attached to each other, but they can also be easily pulled apart, and that's very important in DNA replication. All right, here will help us explain one of our observations in lab. We dissolved an ionic compound, copper sulfate, in both water and ethanol, and we saw that the water dissolved the copper sulfate, but the ethanol didn't. And this has to do with that weak intermolecular force. And in this case, it is between the dipole of a covalently bonded water and then the ions of an ionic substance. So water is actually able to pull apart the ions and surround them, and this is called dissolving. Ethanol wasn't able to do that, and so we know that the dipole in an ethanol molecule is not as strong as the dipole in water, and so water is able to overcome the attraction between sodium and chloride ions, pull it apart, and dissolve it, where the ethanol, its dipole was not strong enough to do that. So it wasn't a good solvent for an ionic substance. All right, so the weakest, the last of all the intermolecular forces is called London dispersion force. And this happens in all molecules, but for molecules that have no dipole, this is the main force that holds them together. So if I have two chlorine molecules, their electronegativity difference, of course, is 0. So what keeps the particles together? What force? It's this dispersion force. So here we have chlorine. Actually, chlorine is a gas at room temperature. I don't know why that says liquid. And so what keeps those gas particles together? So here we have a model of two different molecules. Molecule A, you can see the electrons, they are shown as dashes. And what happens in dispersion force is that the electrons are usually equally distributed around the positive centers of the molecule. However, we know this is a probability, so it also is likely for them to be not equally distributed. And so we see in A that temporarily the electrons distribute themselves on the right-hand side of molecule A, causing that side of the molecule to be temporarily, not permanently, temporarily negative. And then when those negative charges push the other molecule that's close to its negative charges away, and so the side closest to it becomes temporarily positive, just like the balloon that we charged. If you push it on the wall, it will push away the positive charges and then push away the negative charges, leaving the positive charges. So they will be attracted to each other, but just temporarily, because the electrons will redistribute themselves. However, if you have lots and lots of molecules like we do in any substance, then we know at any one point some of the molecules will be attracted to each other with this dispersion force. And that's why it's very weak, because it is temporary. And so if we see, if we look at the halogens, we know that the dispersion force is greatest when you have the greatest number of electrons. So iodine, because it's the largest of all the halogens, has the greatest number of electrons, which is shown in the electron cloud diagram. And so if those electrons disperse each other, that will be a really negative charge. And so the intermolecular force for iodine is much greater than the intermolecular force for chlorine or fluorine. And we can see this by looking at the melting points. All right, so remember, all compounds have dispersion force, and dispersion force gets greater with a greater number of electrons. So let's ask ourselves this quick question. Were you paying attention? Which halogen will have the greatest boiling point? And so go ahead and stop the video for a second and see if you can look at your notes and figure it out. All right, here's a graph. If we graph the boiling points and melting points of the halogens, we see that fluorine has the least, it has a negative boiling point, so that explains why it's a gas at room temperature, and iodine has the greatest, and that explains why it's a solid at room temperature. Bromine is a liquid, and chlorine is also a gas at room temperature. And so this just confirms the idea that we know that the greater number of electrons you have, the larger the atoms in the molecule are, the greater the dispersion force. All right, so reviewing, strength of the IMS. Dispersion force is the weakest, and then dipole-dipole attractions are greater, and then the greatest intermolecular force is the hydrogen bond. We're not going to study that last one. All right, in summary, Dipole-dipole attractions are on a weak force of attraction between polar molecules with a permanent dipole. Hydrogen bonding is a particular kind of dipole-dipole. Again, it's a weak force of attraction between polar molecules, but this time you have to have a hydrogen with either a F, a O, or an N bonded to it. This is the strongest intermolecular force. And then London dispersion forces, a weak attraction, the weakest of all the IMFs, and it's caused by a temporary dipole that develops because electrons are temporarily on one side of the molecule, causing that side to be negative. All right, let's go back to our penny activity. So why did the penny hold more water than alcohol? Well, we know that the intermolecular force between water must have been greater than the intermolecular force between the alcohol molecules, which meant that the droplet on the penny could grow larger before the force of gravity caused it to fall off the penny. So that, my friends, is intermolecular forces, really important everyday phenomenon that affects our life.